All right, welcome. Today, we're diving into the incredible hidden connections between the fuel in your car, the bottle you drink from, and, get this, the scent of a pineapple. It all comes down to the amazing world of carbon chemistry. Let's jump in.
It sounds like the start of a weird riddle, doesn't it? But trust me, the answer unlocks the mind-blowing power of a single element. By the end of this, you'll see exactly how carbon chemistry is the thread that ties all these different things together. So let's kick things off with the absolute star of the show, carbon. You've got to think of it as the ultimate Lego brick of the universe. It's the foundation for, well, all of life, and it's the basis for pretty much countless materials we use every single day. Okay, so when we're talking about organic compounds, we're basically looking at two big categories. On one side, you've got your hydrocarbons, super simple, just carbon and hydrogen atoms, that's it. Then on the other side, you've got your non-hydrocarbons, which are a little more complex. They start with carbon and hydrogen, but then they bring other elements, like oxygen, into the party. And this is where it starts to get really interesting. Saturated hydrocarbons are kind of like a full parking lot. Every carbon is holding hands with another atom through a single stable bond. There's no more room. But unsaturated hydrocarbons, they have at least one double or even a triple bond. And that bond is like an open parking space, just waiting for a chemical reaction to happen. It makes them way more reactive. Okay, so we've got the basic blueprint of these carbon compounds, but where do we get them from in the first place? Well, for that, our journey starts deep underground, with a substance that's literally been millions of years in the making. Yep, we're talking about petroleum or crude oil. This black gold is basically a chaotic, jumbled-up library of all sorts of different hydrocarbons, a real chemical soup made from ancient life. So our first job is to somehow sort through this mess and bring a little order to the chaos. And the way we do that is with a clever process called fractional distillation. Just imagine a giant molecular skyscraper. We heat up the crude oil, and all the different molecules turn into vapor and start to rise. The smallest, lightest molecules, like gasoline, shoot all the way up to the penthouse. But the big, heavy ones, like the bitumen for roads, they barely get off the ground floor. And this right here lays it all out for you perfectly. It's a really predictable pattern. As the carbon chains get longer and the molecules get bigger, their boiling points go up, they get thicker and goopier, that's viscosity, and they get darker in color. Simple as that. But here's a problem. What if we have too many of those big, heavy molecules, and we really need more of the smaller, valuable ones, like gasoline? Well, that's where cracking comes in. It's literally like taking a huge Lego brick and smashing it into smaller, more useful pieces. And this isn't just a neat chemistry trick. It's absolutely essential to meet the world's demand for fuel and plastics. All right, we've got our building blocks sorted. Now let's meet the families. See, just like human families, these compounds share similar traits and behaviors. And if we understand the family, we can predict what its members are going to do. Chemists have a name for this, a homologous series. It's just a fancy way of saying we're grouping compounds that have similar structures and chemical properties. Think of it like a family tree for chemicals, where each branch follows its own set of rules. And every family has its rules, right? In chemistry, it's the same deal, but the most important rule is the functional group. You can think of it like the special tool on a Swiss Army knife. It's a specific bit of the molecule that gives the entire family its unique personality and dictates how it's going to react with other chemicals. So let's meet the main players. Take a look at that functional group column. That's the magic ingredient. Alkanes are stable because they only have single bonds, but alkenes with that CC double bond, way more reactive. And then you have the others, like alcohols with their little OH group, which, as we're about to see, is a total game changer. Okay, we've met the cast of characters. Now for the action sequence. Let's see how chemists can take these compounds and totally transform them, creating brand new substances with all sorts of amazing properties. Remember that double bond in alkenes we talked about? That right there. That's the gateway. Unlike those stable, boring single bonds in alkanes, this double bond is a point of reactivity. It's like an open door, just inviting other atoms to come in and join the party. It's the secret to making all kinds of cool new molecules.
And you can literally see this happen with your own eyes. When we take an alkene and add it to some brown-colored bromine water, that reactive double bond just snaps open. And the bromine atoms, they don't hesitate. They jump right in and attach themselves to the carbon chain. We call this an addition reaction. And boom! Look at that. The brown color is just gone. It turns completely colorless. And why? Because the bromine is no longer floating around it's become part of the alkene molecule. This simple color change is proof positive that we had an unsaturated compound to begin with.
Now, for another really cool transformation, something called esterification. This is where chemists get to play matchmaker. We take a carboxylic acid and an alcohol, mix them together, and they form a brand new compound called an ester. And esters are famous for one thing: their smells. They're responsible for the sweet scents of fruits like bananas and, yep, you guessed it, pineapples.
But wait, there's more. Just when you think you've figured carbon out, it reveals another layer of genius. It turns out it's not just about what atoms are in a molecule, but how they're actually put together. This is what leads to an almost infinite diversity of substances, all from the same basic parts.
The concept is called isomerism. Isomers are molecules that have the exact same list of ingredients, the same molecular formula, but they're built in a different shape. It's like having the exact same pile of Legos, but building two totally different models.
This is a fantastic example. Both molecules you see here have the exact same formula, C4H10. But look at the one on the right. See how it has that little branch sticking out? That seemingly tiny difference in structure can completely change a molecule's properties, like its boiling point or how well it works as a fuel.
And that brings us right back to our original question. The smell of a pineapple? That's an ester made from an alcohol and a carboxylic acid. The plastic in that water bottle? That's a polymer, a super long chain made from alkenes. And the gasoline in your car? A carefully blended mix of alkanes. See? All of these incredibly different things are born from the same family of carbon compounds, just sorted, cracked, and rearranged in clever ways.
So, when you get right down to it, carbon truly is nature's ultimate Lego brick. It can be snapped together in countless combinations to create this incredible variety of substances that make up our world. It really just leaves you with one question, doesn't it? What are we going to build with it next?